All right, well, welcome everyone to the fifth in our series showcasing the Digital Scholarship Lab. I'm Andy Ashton, I'm the Director of Digital Technologies here in the library. I'm going to introduce Jill in just a minute, but I just want to say this series is about bringing in Brown faculty and outside visitors to talk about how technology, and in particular data visualization and analysis, impacts their research and teaching and learning opportunities for their students. Next week, we have two events. On Tuesday, April 30th, Andy Van Dam will present on his history of tool building for scholars and educators, and will demo his latest projects featuring novel interaction and visual presentation techniques within hypermedia frameworks, and that's here at 5:30 on Tuesday. And then again at 5:30 on Thursday, May 2nd, Sean Greenlee from RISD will present on an ongoing electronic art project, and I don't have it in front of me. I think it's called Graphic Sound, and it is a interpretation of imagery as sound using computational techniques. And he is I believe he was a PhD student here at Brown and now teaches at RISD, so that should be really interesting. But tonight we welcome Jill Pipher. Jill is the director of ICERM, the Institute for Computational Experimental Research in Mathematics at Brown. She's been teaching at Brown since 1990 and received her PhD in mathematics from UCLA. Her primary area of research is harmonic analysis and its applications to elliptic partial differential equations with non-smooth coefficients. She also has research interest in cryptography, and in particular in lattice-based cryptography. So welcome, Jill.
So first of all, thanks a lot for the opportunity to be here and to tell you a little bit about ICERM, which is all about the interaction of mathematics and science and the computer, about the interface of math and computation. And so this is 2 blocks from here, in case you haven't had a chance to stop in. It's very close to campus. It's at 121 South Main. And what ICERM does is run research programs that bring scholars from all over the world, including visiting faculty, graduate students, and postdocs to gather in research areas that foster the interaction of mathematics and the computation. So what I'd like to do is tell you a little bit about how that interaction takes place, both from some classical examples, some of which you're familiar with from the popular culture, I'm sure, and maybe some others that you're not so familiar with. So let's start with some of the classical examples. They include fractals, something called the 4-color theorem, the Kepler conjecture, made in 1811, having to do with sphere packing, and the Riemann hypothesis, the most famous unsolved problem in mathematics. And all of these things have some interaction with the computer. So this is a famous picture. This is the Mandelbrot set. This was studied by Mandelbrot by computer experiments initially in the 60s and 70s. So one of the striking things about this set is that it's at all scales it looks the same. It has this self-similarity property. Boundary is what's called a fractal, and in fact Mandelbrot coined the term fractal to describe a boundary that really is not a line bent, deformed into a smooth curve. It's really something of a higher dimension than a line segment, which is dimension 1. Mandelbrot also popularized the concept of fractals and also stressed the importance of this concept by showing people that this was really what was naturally occurring in nature. As I think he once said, that mountains are not cones, and there's a whole lot of objects occurring in nature which can't be described by simple geometric shapes. Really, the fractals are the naturally occurring shapes in geometry. So the thing that's remarkable is that you start with a very simple dynamical system, it's called. You start with a point on the complex plane. So you can think of this as a point on the plane, and you perform the squaring operation, and you add this number c, where c can be anything. And so you jump around on the complex plane from point to point as you square, and then you repeat the process from that point, and you go to another point. And this is this dynamic process. And so the Mandelbrot set is what you're asking about when you ask if something's in the Mandelbrot set. C, the number c, is in that set if, as you jump around, you never wander off to infinity. Some orbits will wander off to infinity, and some will stay within some locus. So for example, if you take the number c equals 1 and you always start at 0, that sequence is going to get bigger and bigger and bigger, so 1 is not in that Mandelbrot set. Now, this was the first picture that Mandelbrot ever saw of this set. That was what things looked like in 1978. Today, people are still looking at dynamics and problems in dynamics. But now what they're finding is that it's not that they're telling the computer what the properties of this set are and getting the computer to draw this picture. What they're doing is they're learning from the visualizations that the computer provides what some of these properties of sets are. So this is what dynamics looks like today, and this was the subject of one of the programs that we had at ICERM in the spring of 2012, and it brought some of the most famous people that are in this subject that have made major contributions to it. John Hubbard was one of the people that originally worked on the properties of the Mandelbrot set and actually mathematically developed and described them. And Jean Yacoz was also here for the program. He's one of the people that he's won a Fields Medal in mathematics for his work in dynamics. So now the next subject that I'm going to turn to has to do with using computers to prove theorems. Now, if you think about what a theorem is, you think, well, maybe so you could be of two minds on this. You could think, well, it should be sort of automatic, right? You're starting from a collection of axioms, of things that you believe to be true, and you're just proceeding step by step and reasoning until you reach the desired conclusion, and so there's something that might be automatic about that. On the other hand, when you really think about what's happening at this level of mathematics, at where we are now with centuries of material built and developed, mathematical proofs start at a pretty high level. They assume lots of background, lots of theorems, lots of definitions, and they're starting at this very deep level and going deeper. So how would you really automate that process? Well, you can't, so you can in some senses, and that's what I'm going to describe, but the first thing you can do is get a computer to help you prove that something is true. How can a computer do that? Well, one way a computer can do that is by performing a calculation which is so long and so complicated that no human could do it in their lifetime. And that was the case with this first computer-assisted proof. So the very first computer-assisted proof has to do with the following conjecture. In 1852, the conjecture was you take any map. So really, we're not putting a lot of constraints on this. Any map that has, you're subdividing something into regions. You can color the map with just 4 colors so that no 2 adjacent regions have the same color. You can imagine that's pretty hard to prove because you're talking about any map whatsoever. How would you even get a hold of the starting point on proving something like this? Well, in 1976, Appel and Haken gave the first proof. And what they did was, well, they did it, so what you might imagine, how would you prove such a thing? Well, you've got to take your maps and you've got to characterize them with certain properties, So any map with this property will have this statement be true, or any map with this property. But there's so many different things that you have to check that there was no way that they could do this sort of by hand. So So there was a certain amount of analysis that was carried out by hand, and then there were lots of cases that were considered that, that required a computer. So there's some more chairs up here if you want to venture into the front. You can even sit on the floor if that's more comfortable, but please feel free to. Okay, so this is any map. So any region whatsoever has this property, and the only reason we know this is true is because of this computer-assisted proof. And so this created a philosophical dilemma for mathematics and the mathematical community. What constitutes a proof? How do we really know if no person can verify this, that something is actually true? That's the whole point of a mathematical proof, is to tell you that beyond a shadow of a doubt, this is true. So, so a little bit later, in 2005, Gonthier tried to resolve this question by going one step further in this. We can't get a human to verify this fact, but Gonthier created a fully formal computer proof of this fact. What's a fully formal computer proof? One that starts at the axioms. One that starts with the axioms of set theory, the empty set is a set, the union of two sets is a set, and develops all of the mathematics in a formal way to sort of plug in the hypothesis and check that the conclusion is true. That took years of work to develop, to put in the definitions, to put in all the things that the computer would require. So now there's a piece of software that you can put on any computer and say, is this theorem true? And the computer will say yes. And so you have more certainty, maybe, that the computer is true, that this is true. He wrote, although this work is purportedly about using computer programming to help doing math, we actually expect that most of its fallout will be in the reverse direction, using math to help program computers. So the next classical subject is sphere packing. So here's the question. What is the densest possible packing of spheres in a given region? All right, so I think this has made it into the popular culture in a lot of different ways. There are actually some interesting applications of knowing the answer to this question, which I'll tell you about in a minute. In dimensions 1 and 2, it's pretty easy to find out what the densest packing can be. Dimension 3, it's really hard. And in dimensions bigger than 3, it's not known. One of the applications of understanding what the densest packing is noisy communication. You want to send some information as a string of numbers, as a high-dimensional array of numbers, and but there's going to be some noise involved as it goes over a channel. So now you have these two strings of information going over a channel, and you want to know how far apart you have to make them to be able to separate their signals. You don't want to have this overlap, but you want to optimize your procedure, so you want the densest possible arrangement. So that's that's a reason to understand the high-dimensional version of this question. So the Kepler conjecture was the conjecture for 3 dimensions. It stated that the densest possible packing is what you might expect, the grocery packing. Think about the grocery packing of oranges, right? The face-centered packing, the one that nestles in between so it touches all the faces. The natural one is the densest possible. Well, so in other words, there's going to be so there's a random packing. How do you generate a random packing? Take a cylinder, for example, a box, and pour some ball bearings, all of different sizes, into it, and measure the density. In fact, that's how in the 1960s they actually figured out what the density of a random packing was. They did these experiments with ball bearings and cylinders, and the answer is that right around, you pour some ball bearings in the cylinder, and the packing is the density is roughly about 0.6. And if you take the cylinder and you shake it a little bit, the density can move up to about 0.64. But if you get above 0.64, it looks like a phase transition has taken place. You've gone from some kind of disorder to order. So the maximum density in 3 dimensions is the density of that face-centered grocery store packing. It's 0.74. And this was proven for the first time by Tom Hales in 1998. Now, this 1,000-page paper contained a lot of analysis that reduced the problem to 100,000 linear programming problems involving 150 variables that had to be carried out on a computer. The article was refereed by a 12-member panel of mathematicians who, after several years, announced that they were 99% sure that the theorem had been proven. So Tom Hales is now busy doing what Gonthier did for the 4-color theorem and producing a fully formal computer proof, which he expects to have ready this year and has been working on it since 1998. Besides communication, applications of sphere packing in 3 dimensions, knowing what the answer is exactly in 3 dimensions, has actually applications to things that some of you might be more familiar with. So sphere packing, is an aggregation of cells. It's clusterings of platelets, if you want. And the number of cell-to-cell contacts depends, of course, on the spacing. It's affected by rearrangement. So, for example, if you know that a random packing has density 0.65 and your maximum density is 0.74, you can do things like measure the effects of medication on clustering. If you're at 6.64 and below, you can assume that you have a disordered collection and there is no actual effect here. And the and speaking of phase transitions, this is one of the main subjects of a program coming up in the spring of 2014, spring of 2015 at ICERM. So yes, we do plan a couple of years in advance for these. So this program features participants here at Brown, like Rick Kenyon in the math department, as well as, and Govin Menon in the applied math department, as well as Charles Radin, who is a mathematical physicist at the University of Texas, who is interested in the physical issues about phase transitions between liquids and solids, and has proposed recently a new means of defining this physically. So you might think that these questions that are so basic have completely been settled and understood, but that's not the case. There are all kinds of interesting issues left in this matter. Now, so these pictures were taken from this simonsfoundation.org website, where they have a lot of very nice stories about what's happening in science in the news. So I highly recommend it if you haven't checked that out. And I can't possibly give a talk like this without talking about Riemann's Riemann hypothesis and the Riemann zeta function, because it is the most famous unsolved problem in mathematics. So Riemann, that's the original manuscript where he wrote down some of these, wrote down this conjecture. So Riemann is a mathematician working the paper was written in 1859, and the question, the object of study, is a certain function that's defined on complex numbers, or in the plane if you prefer. And it has to do with where the function takes on the value 0. And it's a hard question because there is no nice formula for this function. You can write down some formulas for it, but in order to write them down, you have to use infinitely many things to sum up and so forth. So there's no nice closed formula for this function. And there's also infinitely many zeros. So it was actually Riemann himself who provided the first computational evidence for this conjecture, by hand, of course. We've collected a lot of computational evidence for this conjecture since. Why do we care? Well, the Riemann zeta function, its values and the location of its zeros, first of all, encodes information about prime numbers of all things, right? So prime numbers are just the building blocks of the integers. And so the Riemann zeta function tells you something about the structure of the counting numbers. And also lots of other mathematical statements would follow from the truth of the Riemann hypothesis. And the zetas, this particular function, has been shown to be connected to a lot of other interesting phenomena. So, for example, if we look at how far apart the zeros are, so the conjecture is that all the zeros that are not trivial lie on a certain line. They just could, that the 8 billionth zero is on this line and just goes on like that forever. There's infinitely many of them. And then you can look at how far apart they are. And a mathematician named Android Lisko used high-performance computing in 1987 to compute as many zeros as he could at that time, which was about 10 to the 12th. And they're all on that line. We have a lot more. I think the current record is somewhere around 10 to the 22 zeros we've computed. And they're still on that line. So are we feeling 99% sure that they're all on that line? No, because there's other mathematical evidence that also comes from computation which says that if the zeros were not all on that line, the first example of that would be around the 10 to the 30th one. So we're not quite there yet. Interestingly, as a part of these experiments, as a part of these numerical experiments to see where these zeros are and how far apart they are, numerical evidence was found that link these spacings of these zeros with things having to do with models for energy level distributions in particle systems. And so that the spacings of the zeros of the Riemann function exhibited a certain property which has now become known as universality. And universality is a property of complex correlated systems. So, for example, the universality exists in atomic spectra. So now we have this connection between these sort of fundamental properties of particle systems and the spacings of the zeros of this Riemann zeta function, which encodes information about prime numbers. It's just mind-boggling, right? What does this have to do with the bus system in Cuernavaca? Well, it turns out that that was a complex correlated system. Why was it correlated? Well, the bus drivers, as they were coming through, had information about when the bus ahead of them was arriving, and they were slowing down or going faster depending on what that arrival time was. And somebody decided to time the bus arrivals and found out that indeed it exhibited the spacings of universality of this complex correlated system. Yes?
What is universality?
It has to do with these spacings, right? So it has to do with this pattern of, so I'm comparing it to random and I'm comparing it to periodic. I know there's much more involved, but
seems random.
It seems random, but it's not quite random. It has a few other technical properties. Okay, so now I'm going to change topics to somehow a more modern look at some discoveries and experimental directions in math. So I've got a bunch of things I want to show you. I'm going to take some of them really quickly, and some of them take a little more time because I've got a couple of movies I want to show too. So I want to tell you about the three-body problem, about rapid computation of digits of pi, about the polymath project, about modeling an algorithm used from a biological process. This is observing a biological experiment and learning how to make a computer algorithm from it. Extracting useful information from large streams of data, like social networks. the Gracias and Menon self-assembly laboratories, the Mahadevan laboratory at Harvard, and finally the movie Computer Graphics, Math in the Movies. Okay, so the three-body problem for equal masses. All right, so you have three equal masses, you put them in space, you specify their position and velocity, and then you turn on Newtonian mechanics, which governs their motion. When you do this pretty randomly, you find out that most of the orbits of these things are pretty chaotic. There's just no regular pattern to them. But one exceptional orbit of a planar, that means they're all in the same plane, of a planar gravitational three-body problem was actually suggested by a computer experiment. In 1992, Moore produced simulations which produced this figure 8. It lay dormant for a while and was rediscovered and actually proved, and the solution was found by Chensener and Montgomery later. This stable solution was totally unexpected. It emerged from a computer experiment. The digits of pi. Okay, so pi, this irrational number, has infinite, non-repeating decimal expansion. You could also, instead of expanding it using all the numbers 1 through 9, you could also expand it in binary, using just zeros and ones. Now, Hellman-Ferguson is the architect of an algorithm which created, in the hands of Borwein and Bailey, a new formula for pi. You know, something that hadn't been discovered before. There's lots of different formulas for pi that relate the number pi not just to the area of the unit circle, but to lots of other mathematical expressions. This particular formula permits us to calculate the billionth digit, binary digit expansion of pi without knowing the previous one. One practical application of this is asking a piece of software or hardware to compute high digits is being used to provide evidence of integrity. So there's an actual practical application of it. Hellman-Ferguson is also an artist. In fact, that's primarily what he's spent his time doing in the last 20 years. And this is some of his mathematical art. These sculptures are on exhibit at the National Science Foundation, at NIST, at various colleges and universities. And some of them are actually quite large. I think there's a picture of him installing the one at the bottom there in the left corner. The polymath experiment. So this is interesting. So in 2009, Tim Gowers, a mathematician in Cambridge, launches polymath. So his idea is, as in life imitating art, mathematicians are going to imitate computers. These are massively collaborative projects facilitated by the internet. He writes, if a large group of mathematicians could connect their brains efficiently, they could perhaps solve problems very efficiently as well. So he gets hundreds, now thousands, of people working on a single problem. And the rules for engagement are that, you know, you could make incremental contributions. Thoughts are tossed out. Someone says, what about this? And someone else says, what about that? You go down a path, leads to a dead end, you go back and start again. So it really is this sort of massively collaborative, similar to computer interaction. And the first problem was actually solved and has hundreds of authors. And it was submitted and accepted. There's a link to the wiki discussion. And the interesting thing too here is that now you get to see actually the contributions of it that everybody made to the discussion and to the solving of the problem. There's no doubt about who was involved and how. So there's another problem on sorting. If you're interested, you can jump in where it's just starting. Okay, this this is an interesting article that I came across almost by accident. Most of the time I don't have time to sort of flip through Science magazine, but I happened to be intrigued by something and saw this article written by a group of people on the following question. So you have a network. So think of a really large network like the internet. And you're asking the following question: I'd like to find the nodes in this network that are not connected to one another, but are still connected to everything else. I'd like to be able to have the sort of maximally independent set of nodes, the backbone of the router. That's what you're looking for. So it may not be unique, but if the network is really huge, it's really hard to find. And you'd like an algorithm that sort of finds this backbone of this router. So these large networks, right, model things like biological problems, clustering of cells and so forth. And so what they did was they observed an experiment. They observed platelet clustering, and they observed an experiment in which they learned certain things from the biological experiment and applied that into create a new algorithm. So it sort of reversed the model entirely. Usually, you're creating an algorithm so you can analyze something that's going on in biology or physics. Now they're looking at the experiment and saying, what can I learn from how it works in real life, and adapt that into the actual computer science algorithm that I'm creating. All right, so big data. Big data is something that everybody's talking about now. It's, well, and for good reason. It's a part of, we're awash in big data, and we have to have a way to analyze it. We get data from large-scale experiments. We get data across the internet. We get data from social networks. We get data from environmental surveillance. And as we saw last week in the unfortunate incidents in Boston, the ability to analyze large amounts of video and photo data is essential. And we have now software that can do things like facial recognition and give us information in an amount of time that no human being could, faced with the same amount of data. I'm going to give you a more lighthearted example of the kind of information you can get from, say, social networks in just a moment. Last spring, ICERM was host to Brown University's Day of Data, which was organized by Jan Hesthaven and other people in the Office of the Vice President of Research that brought researchers from all across campus, from all different disciplines, to ICERM to talk about how data was influencing their research and changing the directions of their research. So I don't know if you've seen this, but this is an analysis of Twitter feeds over a 24-hour period. And what they're inferring is the mood of the US from these Twitter feeds, from picking out keywords from these Twitter feeds. And as you can see, we're a little happier in the morning than we are, and then we get increasingly unhappy as we get ready for work and go off to work. We get very unhappy by the end of the day. The West Coast is generally happier than the East Coast. The Midwest is never happy, I don't think. Well, Washington, D.C. is certainly never happy. I don't think it ever goes out of the red in Washington. Right? Doesn't it? It just never does. Yeah. Okay, so this is a rather large amount of data that does tell you something. And in fact, they're using, people are using information that comes across social networks and Twitter feeds and Google searches to detect outbreaks of flu in advance of other pieces of information. So this rapid transfer of information can happen through social networks. So Govind Menon is a researcher in the Division of Applied Math here at Brown, and I'm going to show you a movie that was made by the National Science Foundation about their mathematical and computational project. I think I have audio. I hope it's not too loud. Do I have audio? No? Don't seem to have audio.
Being able to build and operate small devices is a big deal. Boxes about as thick as a hair release liquid on command. Cell-sized micro grippers retrieve tiny objects. Their structures too tiny to be assembled by any machine.
The remarkable thing is that these structures, they fold up on their own without any tweezers or human intervention.
With support from the National Science Foundation, Govind Menon at Brown University and David Gracias at Johns Hopkins University are developing self-assembling 3D nanostructures. From small things come big ideas.
There is a need in medicine to create particles that are smart, that can target specific tumors or specific disease site without delivering drug to the rest of the body, which limits side effects.
Basically, it just consists of these nice rigid moves.
Menon and his team at Brown figure out how to best design self-folding nanostructures by flattening them out, and work with a number of shapes, like the 12-sided polyhedron, which can potentially fold into a box-like container.
Imagine cutting it out and flattening out the faces as you go along, a two-dimensional unfolding of the polyhedron.
He says not all flat shapes are created equal. Some fold better than others.
The best ones are the ones which are most compact.
They developed an algorithm at Brown to sift through all the possible choices, narrowing the field to a few compact shapes that easily fold into 3D structures. Those designs then went to Johns Hopkins, where they created the physical configuration.
We create structures that have two parts, the face, and then we deposit a material in between the faces and at the edges.
Then they heat them up, creating surface tension that pulls the edges together and fuses the structures shut.
The era of nanotechnology promises to revolutionize our lives. We can make them with a lot of different materials, metals, semiconductors, and even biodegradable polymers for drug delivery applications.
Now that's thinking outside the box. For Science Nation, I'm Miles O'Brien.
Yeah, so that Science 360 series is also a lot of fun. I recommend that. Okay, so I have two more things to tell you, and the next thing following is a movie, and it's about 10 minutes long, so I do want to get to it really soon. So I'll be a little quick here. This researcher is researching morphogenesis, the geometry. So this is a combination of geometry, physics, and biology. And what he focuses on are cell, tissue, leaf, and flower, and is answering some pretty basic questions about problems of growth in both cell and in plant. He's giving a public lecture here on the Brown campus, sponsored by ICERM. Next fall, September 24th, we'll be sending out some announcements. Watch for that. He's a brilliant speaker. Is part of the Mathematics of Planet Earth 2013 series, and this lecture series is funded by the Simons Foundation. And there are 9 worldwide locations for these public lectures in Math of Planet Earth in 2013, and we were selected as one of these locations. So we're very pleased about that. So he talks about he thinks about things like, how do the guts coil? How does a lily bloom? And what he's trying to understand is the exact mathematical process that can be then simulated, and models can be created from this. Now, it was known that there was probably something having to do with differential growth, but he pinpointed the exact place in which the differential growth took place. So the edges are growing faster than the rest of the leaf. and he's provided the mathematical models and simulations. So he's focusing on some really basic things and providing the first answers to some of these questions. Okay, so I'm going to end with something that we've just started at ICERM, which is we have lots of people coming through giving talks, public lectures even, general audience talks to our audiences there, but we decided to try to ask some of these people to give a 10-minute talk to a general audience on what they're doing. So this was the first one we tried, and it was very successful. And I like the fact that I'm showing it to you in here because of this self-similarity process. We filmed it in the Digital Scholarship Lab, so I'm going to show you a movie of somebody talking in here about what they've done. So this is Robert Bridson, and he's from the University of British Columbia.
I'm Robert Bridson, and we're from
So enjoy.
the University of British Columbia. I'll be talking about visual effects. That's the computer-generated imagery that I've seen on TV commercials. That's the physics of motion, and how that plays a role, actually, in visual effects these days. And partly I'm hoping to give you a sense of actually the subtlety and the art and the pervasiveness of the future of visual effects, but also the role of mathematics and the research that we're doing computationally and numerically, and physically and mathematically to get us there. So I'll start with this image. It's from a short film, Nuit Blanche. This is actually from the making of, and I think it tells a wonderful story here, because you get a sense of how this was shot. It's a street scene, but the actors were filmed, instead of on the street, they're filmed in front of a green screen in the studio. And the next step is going to be to somehow take off the green pixels and blend them in for this backing. And it turns out this backing is actually completely digital. It's fake. It's not a real street. You can tell the truck here is not been filled in yet. You might be asking yourself, why? Why would you bother doing this when you could just send a person out with a camera and just film them walking down the street? Turns out that actually is not as easy. It's not as effective. For one thing, this is supposed to be shot 70, 80 years ago. And finding a street that looks like that today with those kinds of street lights and so on, probably very hard. Most likely you'll instead have to redo a whole bunch of signage and bring your own street lamps and everything, or build this in a studio somewhere, which suddenly gets very expensive and difficult. On top of that, you're going to have to fly in lighting people and camera people and your actors and get the city permission and clear out the street and get an antique truck and drive it down and park it, and then hope the weather cooperates. If it doesn't, you have to do it all again. And even if you do get a good take, but then the director a week later comes back and looks at the footage and realizes something was wrong, that's it. You can't do it again. So there's going to be artistic compromises apart from all the expense and difficulties. It's unpredictable working with the real. So it turns out it is actually now the tools that artists have available to them makes it easier for them to build this fully digitally. And I guarantee you, in a lot of films you've seen, TV commercials, TV shows, there'll be an immense number of things that are digital, faked, that you have no idea were. Even though I work in film, I'm constantly surprised by the things that actually weren't real. Here's another shot, which maybe is sort of the more stereotypical side of visual effects. In this case, aliens flying in an alien planet. This is from Avatar, which I worked on a few years back. And clearly, this kind of thing couldn't happen in real life, so obviously it's digital. But I think most people didn't appreciate the fact that, in fact, everything else in this image is digital as well. This is not a real coastline. It didn't fly a helicopter through New Zealand. And the water crashing up against the cliffs is not real as well. That's all digitally simulated. And in particular, my role in here was to actually write some of the software that they use to simulate that water. One of the interesting subtleties about this, and again, the kind of thing you can do when it's fully digital, is that they actually synchronize the waves crashing against the cliff with the background music. Again, you cannot do that in real life. You can get these wonderfully subtle artistic conveyances if you have the control. So again, just coming back to Nuit Blanche, I would really recommend finding this. It's a beautiful short film. You can get it, you can see it on the web. And it also has a making of film, which is particularly nice too, because then you really will get a chance to see everything that goes on in the visual effects side to make works of art. let me drill down a bit deeper into what it is that I bring to visual effects. So my specialty is physics-based animation. So in this case, this is an animation done by Dan Wood. Boats floating in water and the water's moving around. The geometric detail and the complexity of the motion of the water is such it essentially would be impossible to animate that by hand. But we want a digital version. So in fact, what we do, what I bring to the table, is that even though this is highly complicated, we do have a very good understanding of excellent models of physics in play here. That's been developed over the centuries. Computer solutions to those models, the equations that describe the motion of water, have been around now more than 60, 70 years. To actually have a very good understanding of how things should be. And now we've got the computational horsepower that we can actually solve for the motion of the water divided up into 100 million little blobs interacting, which we'll come back to. And we'll get all the realistic detail that should be there just because we're solving the right model for it. And the artist, all they have to do is tell the computer to go somewhere. Okay. Let me dive deeper now still. Kind of, what is it like to actually come up with these models? Well, if you want to simulate something in a computer, you have to tell the computer everything about what it is you're simulating. In particular, if we're going to do water sloshing around a container, we have to specify to the computer what the container is, what its dimensions. We also need to tell it about water. But we need to do more than just say, here's a block of water. We want it to be able to move and develop interesting geometric detail. We have to give it the degrees of freedom it needs to reproduce that. And it's tricky. What is the shape of water? How do you describe water? You could go down to the molecular level, but that's way too expensive for a computer. So we take something intermediate for graphics, typically. And we're going to split up our water into millions of little minuscule blobs of water. So that these could be millimeters or centimeters in size. And we're going to assume that these particles of water, these blobs, just coalesce into the water volume. And that's what we see. But we can control each one of them individually and figure out the physics, the motion of each one. So of course, if we have physics, we need forces to move these around. Gravity is obviously going to be a big part of water. But if that's all we have, then of course it just falls straight through the bottom of the container. So we didn't tell the computer about the forces that prevent it from going through a container. So we can come up with a model for that, saying nothing's allowed to go through the bottom. But if that's all we do, then we end up, well, with just this super dense puddle of blobs on the bottom of the container. And that's still not really what water would do. We need forces that the water exerts on itself. So individual blobs of water are somehow going to interact with all the blobs around them. Now, coming up with a good model for that at the particle level is maybe tricky, but we do have a sense that one of the defining characteristics of liquids is that they conserve their volume. There are a few caveats, sound waves and things we're going to ignore, but by and large, the volume stays the same. So obviously, there have to be forces that cause that to happen. Now, again, talking about particles and volumes is maybe a bit tricky, but we can take a creative jump to the side and instead think about the space that the water is flowing through. So here I've sketched out just this abstract square, or a cube in space. If I measured the amount of water flowing into it at any moment in time, it would have to exactly balance the amount of water flowing out. So the volume is going to stay the same. So I can actually write down an equation that describes this. If I have velocities coming in on one side of the cube, and velocities going out on the other side, they have to add up to be about this balance, which I've written down here as a very simple equation. And this is the key to making water look like water. Now, I still have to deal with particles, so I have to blend these ideas together. So here, I'm going to take my particles with I've drawn red arrows here to say they're trying to fall down. I'm going to splat those velocities onto a grid of these little cells where I can write down an equation in every single one of them. That's a lot of equations, but I've got a powerful computer, so I can ask the powerful computer to solve those. It should only take fractions of a second or maybe a few minutes if it's really gigantic. And I get new velocities that now encode the fact that this is water that conserves its volume. And I can bring that back to the particles and move them around. And I get 1 frame worth of water sloshing. So let's actually see what that looks like. So here I've done exactly that, and these are the results. And this is low resolution and so on, but it kind of captures the feeling of what water should look like. The only trouble is even if it moves like water, of course it doesn't look anything like water. It looks kind of like these little blue beads swirling around. So we need to do something about that. What's missing in the model is some description of what the surface should be like. And this is now bringing us to, say, the cutting edge of research on the graphic side. Just how do you make a surface follow a liquid? So this is something my students and I have been working on, particularly with triangle meshes. So I can describe for the computer a surface in terms of a network of triangles. The tricky thing, though, is when I have water splashing tracked by these triangles, is that water does all kinds of nasty geometric things, like stretching out into super thin sheets. I have to keep subdividing my triangles to make sure that they don't stretch out to crazy sizes. It also does nasty things like bits of water combining or splitting apart, and so I have to do all kinds of complex operations to keep track of that. And the various invariants, and lots of fun but hard geometry problems. Here's just another version. This is with surface tension instead of gravity. You can see some interesting little dynamics here. So I'll finish here. I'm not going to dive any deeper into the math on this. But I guess, again, the 2 points I want to get across. One is visual effects is more pervasive and more subtle than probably you think. Not too far in the future. Anyone with the talent and the story ideas will be able to tell it just using a computer. And on the other hand, give you a sense of the mathematical research that brings together physics and numerics and computer science and geometry to actually make this possible. Thank you.
So I'm going to stop here too, and thank you. Okay.